Fermi's theory of beta decay. This is the most successful theory which explained beta decay completely. Fermi gave his theory based on Pauli's neutrino hypothesis and Dirac's theory of probability of emission of photons. He made certain assumptions before making his theory. The assumptions are the electron and neutrino are created by the transformation of a neutron into a proton in a nucleus and vice versa. That means the transformation of nucleons from one state to another. That means a neutron may change into a proton may change into a neutron. During this process, a beta particle is emitted plus a neutrino or its antiparticles are emitted. This is his first assumption. And second assumption is, we all know in all radioactive nuclear reaction, energy is always a conserved quantity, and in beta decay is also it is assumed the energy remains conserved. And the new particle neutrino is suggested to have a zero rest mass or assumed to have a zero rest mass or a negligible mass when we compare it with the mass of the electron. And fourthly, this beta decay process is analogous to or similar to the emission of electromagnetic radiation by an atom. And the fifth assumption is, we know the nucleons are the strongest, or the nuclear force is the strongest force, or the strongest interaction in the in nature. When we compare it with the electron neutrino field, they are very, very weak. And the time-dependent perturbation theory seems to be a very good approximation for this theory, and there is no nuclear parity change occurs. And finally, we all know the nucleon moves with the velocity of only c by 10 times inside the nucleus. So all the calculations are made with a non-relativistic nuclear wave functions. These are the assumptions made by Fermi before deriving the theory. Now let's get into the theory. So Fermi used Dirac's expression for the transition probability per unit time of an atomic system to emit photons and time-dependent perturbation theory to derive this his theory. So firstly, the chances are what are the probability that an electron having momentum between PE and PE plus DPE that can be emitted in a unit second is given by capital P of PE DPE equal to 2 pi by h cross HIF of mod of HIF square dN by dE naught. This is nothing but this is Fermi's celebrated Fermi's golden rule. So this equation 1 represents that chances of an electron having a momentum between PE and PE plus DPE can be emitted during 1 second or per unit time. So in this dN by dE naught is nothing but it is the number of quantum mechanical states of the final system per unit energy interval, and HIF is the matrix element of interaction for the initial and the final states of the particle. So in equation 1 we have two factors which needs to be found. One is HIF, that is the interaction matrix element. The other one is dN by dE naught. First let us find out what is the interaction matrix element, and this interaction matrix element is defined as HIF is equal to psi f star h, the Hamiltonian operator, psi I into d tau. See, psi f and psi I are the wave functions of the system in its final and initial state. This is the general definition for HIF. So this H is nothing but it is an Hamiltonian operator that explains the weak interaction between the initial and the final state. And d tau is the volume element. Let us consider the negatron decay, in which a neutron transforms to a proton with the emission of a electron and an anti-neutrino. So this is a negatron decay. We know a beta decay happens by three process. In already in one of my video I have explained about beta decay. So negatron decay, positron emission, and thirdly by capture of orbital electron by an atomic nucleus. So negatron decay is one mode of an decay, beta decay process. So neutron when transforms into a proton with the emission of an electron and antineutrino. So we know a parent nucleus is nothing but that is the state of initial state of the system. So here the parent nucleus is neutron, and the daughter nucleus is the product plus what are the particles emitted from the parent nucleus. So the initial state is nothing but the wave function of the parent nucleus. So it is psi I. The next is psi f, that is the final wave function of the final status, the wave function of the daughter nucleus, the wave function of the electron, and the wave function of the antineutrino. So in the product side we have three particles. One is the daughter nucleus, that is proton, other one is the electron, and the third one is the antineutrino. So it is psi f, psi e, psi neutrino bar. So this equation now gets modified. In place of psi f star, we are replacing it by, so HIF is equal to G times integral of psi f star psi E star. It is a written error there. It is psi E star psi neutrino into m into psi I d tau. In place of psi f star, we have replaced it with psi f star psi E star psi neutrino. So when you take star for this, antineutrino, so when you take a conjugate for this antineutrino, it becomes a psi neutrino. And here this constant G is called as in Fermi's coupling constant, which explains the strength of the interaction, and it has a value of 0.9 into 10 power minus 4 MeE, which is almost similar to the role, it plays the role equivalent to a charge of an electron. And here M is nothing but it is a dimensional matrix element and behaves as an operator. It plays the same role as a Hamiltonian. Now let us quickly find out what is psi neutrino and psi E star. So the psi neutrino, the wave function of the neutrino and electron, we are going to find the psi neutrino is equal to e power minus I by h cross p neutrino into r dot divided by root of v. And the same way wave function, the conjugate of wave function of electron is given by e power minus I by h cross pe into r divided by root of v. Here we know this pe and p neutrino are nothing but the momentum of the electron and a neutrino. R is the position coordinate. So the matrix elements gets modified into G into psi f star. So substituting those values, root v into root v becomes v into 1 by v into e power minus I by h cross pe vector plus pr vector into r vector into m into psi I d tau. So let us take that constant v outside. So our HIF becomes G by v integral of psi f star e power minus I by h cross pe bar, that is the vector, plus p nu vector into r vector into m into psi I d tau. This is equation number 4. The exponential factor in the equation number 4 seems to be a troublesome one. Let us reduce that one. So the exponential factor, now we are going to explain, expand it in terms of exponential series. So e power minus I h cross into pe bar plus p nu bar into r vector, that is e power minus x. When you expand it, you will get 1 minus x by 1 factorial plus x square by 2 factorial minus x cube by 3 factorial. It goes on like this using the exponential series. When you expand it, you get 1 minus I by H cross P bar plus PR bar, even though we have not that a vector is not written over P nu, it is again momentum is a vector quantity. P bar plus P nu bar into R vector minus 1 by 2 H square into P bar plus P nu bar plus into R the whole square, and the factor goes like this. When you compare this second term and third term with the 1, they seem to be a very smaller one or a negligible quantity. So this exponential factor can be approximated to 1. Let us substitute the value of 1 in equation 4. When we substitute it, we get HIF is equal to G by V into psi F star M into psi I d tau. So this is the nuclear matrix element. Here the MIF represents the nuclear matrix element of the final and the initial wave functions of the nucleus. So we have found the interaction matrix element. Next we are going to find out the dn by, that is the number of quantum mechanical states available between the final and the initial state. Okay, that we call it as a statistical factor or a final state density. So this dn by de naught is found on the basis of phase space concepts. We know this dn and dn nu are the number of quantum mechanical states available for the electron, that is the beta particle, and the neutrino in a certain volume V. So then this dne, the number of states available, quantum mechanical states available for the beta particle dne is given by 4 pi pe square dpe into V divided by h cube. So this is nothing but this is taken from the statistical mechanics for the number of states states available for a particle. Okay, so by that dne is equal to 4 pi pe square dpe by V into V divided by h cube. In the same way we can write it for dn neutrino, which is also equal to 4 pi p nu square dp nu V by h cube. So the total number of states available is given by dn is equal to dne into dn nu. So substituting the values of dnu and dn nu, we get 4 pi p square dpe V by h cube into 4 pi p nu square dp nu V by h cube. Together we can write, multiplying these two terms, we get dn equal to 16 pi square pe square p nu square dpe dp nu V square by h power 6. So the total number of states per unit energy of the electron. So to get an per unit energy, we are dividing it by dE naught. So it becomes 16 pi square by V square by h power 6 pe square p nu square dpe dp nu divided by dE naught. Let us take it as equation number 7. So the total available energy is E naught, which is equal to the energy of a neutrino plus energy of the electron. For our simplification, let us write E nu is equal to E naught minus EE. Quickly square it, so you get E nu square is equal to E naught minus EE the whole square. We also know E is equal to mc square. So splitting that, we can write m into c into c. So m into c nothing but it is a mass into velocity, that is the momentum, multiplied by c, or in place of E we can write pc. So E nu square can be written as p nu square into c square, which is equal to E naught minus EE the whole square. So p nu square is equal to E naught minus EE the whole square divided by c square. And we also know, we have already wrote E naught is equal to E nu plus EE. For a fixed electron energy, that is EE, when you differentiate it, we say the EE is fixed, that means it is a constant. So dE naught will be equal to dE nu. Again writing E in terms of PC, we get dE naught is equal to C dP nu. So dP nu by dE naught is equal to 1 by C. So substituting this dP nu, dE naught and P nu square in equation 7. Substitute in equation 7, we get dN by dE naught 16 pi square V square h power 6 PE square. In place of P nu square, we are substituting E naught minus EE the whole square by C square into dPE into 1 by C. So dP nu by dE naught, in place of that we are replacing it with 1 by C. So let us bring this C inside. Bringing everything inside, we get 16 pi square V square by H power 6 C cube PE square E naught minus EE the whole square into dPE. So we got the final density factor dN by dE naught. Now let us quickly substitute the value of the interaction matrix and the dN by dE naught in equation 1, that is Fermi's golden rule. We get capital P. That capital P represents the probability. P into PE dP is equal to 2 pi by H cross G square by V square MIF square into 16 pi square V square by H power 6 PE square E naught minus EE the whole square into dPE. And here this V square and V square gets cancelled, and we have a H cross at one place, H bar 6 at another place. We are going to convert all the H's into an H cross, and for adjusting this, we are multiplying and dividing by 2 pi cube, and in the numerator as well as in the denominator. Finally we get the capital P, the transition probability, capital P into PE dPE as G square MIF square into PE square E naught minus EE square, EE the whole square into dPE divided by 2 pi cube C cube H power 7. So this equation represents the chances or the transition probability that an electron can be emitted per unit time between the momentum range PE and PE plus dPE.